Hey guys, welcome to another video. This will be recitation number 9 in linear algebra. I would like to cover some problems from the worksheet, some Putnam problems. So let's get started. But first, let me start with a problem which uses again the Newton's formula. Well, I shouldn't have said that, but anyway. So the problem states the following. In fact, we will use again the eigenvalues of a matrix. All right, so problem 1, and this says the following. So if X is a square matrix, matrix of size n, right, an n by n matrix with complex entries, let's say, such that for any positive integer, let's say k, right? We have that the determinant, so we have this condition of x to the power k plus the identity. This guy is 1. Then show that, so if this holds true, then show that something happens with the matrix. Well, it's basically the matrix is nilpotent, but or we can say that x to the power n is the null matrix, right? So we have this condition here. We'll see this one here. So we have to prove something about this one here. All right. Well, it's quite obvious that this problem will require the use of eigenvalues. So let's do this. So we'll like to translate that determinant condition in terms of the eigenvalues. So let's consider let lambda 1, lambda 2, lambda n be the eigenvalues of the matrix X. All right, so it's easy to see that, well, by the spectral theorem, it is it follows that a lambda 1 to the power k plus 1, lambda 2 to the power k plus 1, and we keep going, lambda n to the power k plus 1. So these are the eigenvalues of this matrix x to the power k plus the identity, right? So by the spectral theorem. So in other words, our condition, so the condition that the determinant of x to the power k plus the identity is 1, will translate into the following. So the hypothesis of our problem translates into the following. So we will have that, I'm going to write it in this way. So the product overall, let's say I from 1 to n of lambda I to the power k plus 1, this is 1. So this is how we translate the condition, because you know that the determinant is nothing else than the product of the eigenvalues. So, okay. And now, let's see, what can we do this? If we expand this, right? So if we, by expanding the above equality, we have, and let's see, what do we have? So we would like to expand this, And now by expanding this equality here, so we will have that, well, I'm just going to write it in the following way. So we're going to have that, how should I say it? That x1 to some power, sorry, x1 to the power k, and I'm going to write it in this way, plus x2 to the power k, plus xn to the power xm, right, to the power k, is 0. And this is where these numbers, x1, x2, xm, so these guys here are the products. So I have just the sum of some products to the power k, so are the products. And what kind of products do I have? I have, let's say, a lambda I1, a lambda I t, let's say, right? With t between 1 and n. And these numbers, 1 is less than I1, I sub 1, and I sub t, and is less than n. And here, keep in mind that this m is 2 to the power n minus 1. All right. So this is how we translate this condition. So we can write it in this way, so by expanding. And now we're in a very fortunate position at this point, because when you have these sums to be 0, then you can definitely apply the Newton's formula. We have discussed this. So let me just say this. So denote, let's say by S sub k, the elementary symmetric sum, symmetric, and let's just say maybe symmetric polynomials, okay. Okay, so the elementary symmetric polynomials defined by, so these guys will be defined, so Sk will be nothing else than just this sum with 1 less than I1, less than I2, less than Ik, less than m. Of these guys, xi1, xi2, all the way to x sub im. And so these are the elementary symmetric polynomials. And in this case, we'll also define pk to be this x1 to the power k plus all the way to xm to the power k, right? Well, it's quite clear that P1, so clearly P1 is the same as P2, and it's equal all the way to Pm, and it's 0, right? And now we're going to apply the Newton's identity. So by applying Newton's identities, and let's just write them. So I'm going to remind you these identities, right? So there are these k times s sub k, which is the sum from I equals 1 to k of, what was it, negative 1 to the power I minus 1, s sub k minus I, pi. Okay, so these are the Newton's identities. So applying this, well, we've discussed one of the problems previously, right, using these identities. So by applying this, let's see, what do we have? So we have that, so we know that this is valid for all integers. So this is for all k greater or equal than 1. So by applying these identities, it follows that, well, if we look at it, you see we have these we have the pi's here. I want you to look at it. Look at these guys here. And we know something about them. Look at them. They're all zeros. So this implies that sk will be 0. So this implies that S1 is the same as S2 is the same as all the way to Sm, and this will be equal to 0, right? And now it's quite clear. So therefore, it follows that x1 is the same as x2 is the same as xm equals 0, and we have that lambda, all lambdas are equal, right? Because these don't forget that this xm were nothing else than just the products of lambdas. So we have that lambda 1 is the same as lambda 2 is the same as lambda n, and the same as 0. So all the eigenvalues of my matrix X are 0. So therefore, this by Cayley-Hamilton, it follows that X to the power n is the null matrix, and that's the problem. That's the end of the problem, right? So again, the main ingredient here was using Newton's formula. This is very important when you have some kind of relations between the eigenvalues. You know about something about the sum, you know about the products. It's very good to use this kind of formula, right? All right, so this is one of the problems, and I wanted to do this one. But now let me veer towards something like some old Putnam problems. In fact, so this was problem 1. Problem 2. Says the following, and this is I would say a tricky, I wouldn't say tricky one, but anyway, so this was a Putnam, what was it? Putnam B1, 1969. Okay, now let A and B be matrices of size 3 by 2 and 2 by 3, respectively. Okay. Right? Suppose that their product in the order AB. So we're going to compute AB, A times B, is given by, and as you can see, the product will definitely be a 3 by 3 matrix. So it's given by the following 3 by 3 matrix. So AB will be nothing else than just 8, 2, -2. What else was there? 2, 5, 4, and -2, 4, and 5. Okay, so this was the matrix, right? So it's a 3 by 3 matrix. And we would like to show that, so show that the product BA is given by and well, this time this will be a 2 by 2 matrix, right? And this matrix will look very simple. So as you can see, it's a diagonal matrix. All right, so this was the problem. It's an interesting problem, but usually there is a standard technique here, and we have to look at something. So what we would like to do is just to be careful with something here. So let's see. Okay. Now, let's look at this matrix. As you can see, I would like, so this is a 3 by A is a 3 by 2, B is a 2 by 3, and this guy is a 3 by 3. Now let's look at this, let's compute the square of this 3 by 3 matrix. We compute the square matrix of AB. So we have that AB squared is nothing else than just, well, surprisingly, if you do the computations, so this would be this matrix 8, 2, -2, 2, 5, 4. That's in fact, usually it's a standard trick, just like I said. And if you compute this, by this, and then I'll leave it to you as an exercise to compute it. It will give you nothing else than just 9 times AB. Like I said, this computation, I don't want to lose my time with this, but it will give you this. That's very interesting. That's the interesting part. So now we're going to do the following. So I know that AB squared is 9AB. And now I'm going to look at the rank of BA, right? So let's look at the rank of BA. So now, let's so the rank of BA by applying the basic properties of the rank is greater or equal than the rank of, let's say, BA times another matrix. For example, we can put any combination here. Let's say, let's put A, BAB. Right, we will always have this. So, but what is the rank of this? Of this guy? Well, you know, it's associative here, so you can say this is the rank of AB squared. But you know that the rank of AB, you know that this is nothing else than the rank of 9 times AB. And I'll leave it to you as an exercise to show that this is actually 2. Well, it's not hard to see. You just look at the determinant of this, so it's quite easy to look. Anyway, so the rank will be 2. So this implies that since the rank is greater or equal than 2, that BA is non-singular. Is non-singular. Okay. Right, so it's invertible. All right, so what does this mean? But, and now let me look at BA, but I'm going to do the following. I'm going to look at BA squared. So BA, everything squared, right? So let's see, BA squared. This would be what? AB. So no, maybe I should look. No, maybe let's look at the cube, because I can write this in the following way. So we will have that BA cubed will be what? So this would be, let's think. So BA cubed, this would be, let's write it in this way, B, right, times AB squared times A. Okay, because I know that AB squared is 9AB. Okay, that's perfect, right? So I can do this. So this would be B times 9AB times A, right? So we have used the first relation. So this would be nothing else than just 9 BA squared. Okay, that's great. So, and well, now it's quite clear that the result will follow immediately, right? Since 9 BA cubed is 9 BA squared. And we know that this BA is not singular, so you can just multiply. It will follow that BA is 9 times the identities. So BA, anyway, I'll leave it to you as an exercise. So it's 9 times the identity to show this. Well, you just multiply by BA inverse to the left, to the right, whatever. You can reduce it. You have BA squared, it will be 9BA. Then apply again the you multiply it to the left by BA inverse again, and we get this. Anyway, that was a tricky one. Well, the trick is not. You just have to look at the ranks. Anyway, so that was a Putnam B1 in 1969. Now let's do another one, another simple one. Problem 3. Again, this was a Putnam, I think, Putnam A2 in 1991, which says the following: let A and B be different n by n matrices, right, with real entries, if A cubed is the same as B cubed and A squared B is the same as B squared A, then it's a question, then can this matrix A squared plus B squared be invertible? That is a question we would like to ask. So is this matrix invertible? Well, well, let's assume, well, we will show that the matrix, this A squared plus B squared, so, right, is not invertible. Right? Okay. So assume by contradiction that this matrix is invertible. Right? All right. Well, then the inverse exists. Okay. So what we're going to do is the following. So we're gonna, how about we can do a magic trick. So what we're going to do is we let's multiply. So so we have the following. So I know that A and B and B are different. So what I'm going to do is that I'm just going to multiply A plus B, A squared plus B squared, right, times A minus B. And once we do this operation, let's see what do we have here. So we have A cubed minus A squared B plus B squared A minus B cubed. Well, and probably you'll see here that well, with giving these two relations, so this would be, this is the null matrix, and again, this will be the null matrix. So this will be the null matrix. Yeah, but I know that A is invertible, so the only option I have is that, so this implies that A minus B is the null matrix, or A equals B, which is a contradiction. So this is false. So where did the contradiction come from? So from our assumption right here, that A squared plus B squared is invertible. So it follows that the matrix A squared plus B squared is not invertible. And the problem ends here. So that was a Putnam 8-2 in 1991. Pretty easy, I would say. And it's also in the worksheet that I'm having here, that I assigned for you to solve. Okay. Now I'm going to do another problem. So problem, what's the number of problem 4? I think I'm probably going to stop. This one was a very recent one, so it's given at this, I think I've told you, this worldwide Putnam type competition, which similar to Putnam. It has 2 days, 5 problems each, so it's all organized in Bulgaria every year. Anyway, and many universities, especially in Europe and even around the world, participate in this. So this was an IMC. So this was an online this year for obvious reasons. So this was an IMC 2020, which says the following. So let A and B be n by n matrices such that we have the following, such that the rank, we have this condition, the rank of this matrix, AB minus BA, I think we've met a couple of times with this matrix, plus the identity is 1. All right, where, you know, IN is the identity matrix. Now we're asked to prove that the trace of, so it was stated in the following, AB minus the trace of A squared B squared is 1/2 n times n minus 1. All right, so this was the problem. Well, probably as you already guessed, so let's come up with some notation first. Let me denote this matrix. Well, I can denote, so let bracket AB be this matrix AB minus BA, right? And we know that, so we know that the rank of this matrix, let's say this matrix bracket AB plus the identity is 1. And we have done a lemma which says that if I have a matrix of rank 1, so this is a matrix, let's denote this by X. So keep in mind that a matrix, an n by n matrix of rank 1, you can write it in a very nice way. It definitely basically says that x squared is the trace of x times x. So by a previous lemma, this was done, I think, in course in lecture 9 or 9.1. Anyway, you can look it up in one of the videos. So by a previous lemma, it follows that x squared is nothing else than just the trace of x times x. All right, so let's see what this happens. So keep in mind that x is the bracket. So this, and thus we have that this bracket AB plus the identity squared is nothing else than just the trace of the bracket plus the identity times the bracket AB plus the identity. Okay, and now let's rewrite this this relation here. So this would be equivalent with, let's keep this term on the left-hand side the way it is. So this is AB plus the identity, everything squared. So, and now let's do something about this trace here. So as you know, this is nothing else than just the trace of the bracket. And you know what happens with the trace of the bracket plus the trace of the identity. And this is this. This guy is 0, we know that. The trace of the bracket will be equal to 0. So this would be equivalent with the bracket AB plus the identity squared is nothing else than just n. The trace of this guy is n. So this is n times bracket AB plus the identity. Okay, now let's do some more computations here. So this would be equivalent with, this guy is AB squared plus 2AB, right? Plus the identity equals n AB plus n times the identity. So we have this relation. But now we have to prove something, and keep in mind that we have to prove that the trace of AB. So maybe we should look for this guy a bit, to expand it a bit, because we know how these two guys behave. So we know how this guy behaves, we know who this guy is. So our intention is to take the trace again, perhaps. But now, before I go and do this, I want to write this guy. So this is AB. I'm going to write it with red. So AB minus BA, everything is squared. And I would like to expand this. So this would be AB squared minus AB BA plus BA, everything. Wait. Minus BA AB plus BA squared. And now we're in the position of applying the trace. So by applying the trace, we have. All right, then let's be careful here. So we look at this equality above and we apply the trace there, right? So we have that, you see these guys, this guy here and this guy here will just go away when we apply the trace. So that's it, they're gone. So that's the good thing. So we have that the trace of AB squared minus AB BA minus BA AB plus BA squared. All right, so this is the first term, plus N equals N squared, right? Because the trace of N times the identity is N squared. All right, that's great. And this guy will be equivalent with, and now let's be careful here. So the trace of AB squared plus the trace of BA squared minus, and now let's see what this is, minus trace of AB BA minus trace of BA AB is the same as N squared minus N. And now it's quite clear what happens. Now these two guys here, this guy, and these guys are the same, so they're equal. And this guy here and this guy, they're also equal as well, right? And this would be, well, AB squared, so this would be equivalent with, let's write it. This is equivalent with saying that 2 times trace of AB squared minus 2 times trace of AB AB right? AB BA, let's say, right? Okay. Okay, this would be nothing else than just N squared minus N. And now you can write this as trace of AB squared minus trace of AB BA is N times N minus 1 over 2. But now, well, is this equivalent with the same thing? Well, it is. You can, for the first term, it was AB, which was AB squared, right? So this guy is the trace of AB. And this guy here is the trace of, if you want to, because the trace, you know, with when you commute this, is that you can move A in front of it, so it will be the trace of, you can move the A on the last A, or you can move it on the left, so this would be the trace of A squared AABB, or A squared B squared, which is exactly what we wanted to prove, and that's the end of the problem. Okay, guys, I think I'm going to stop here with the recitation. I think next time I would like to talk about, we'll talk about some special topics in linear algebra, such as diagonalization. I will talk about the Schur's theorem, how to triangleize matrices. We'll talk a bit about the Jordan canonical form. That will be very interesting. And well, we'll do some applications. You'll see that these techniques are very, very useful. And unfortunately, they're not taught in any undergraduate, at least not in the standard undergraduate course in linear algebra. Unfortunately, the course stops, well, usually after a little bit about diagonalization and maybe a bit about orthogonal diagonalization, the course just stops there. So no talking whatsoever about the simultaneous triangulation or about the Jordan canonical form. But anyway, We will talk about this in lecture number 10. All right, thank you very much.